algebraically integrable systems. Then you just can find position of particles at moment t by solving not differential, but algebraic equation. I am again insisting algebraic because it's like finding roots of some function. Theta, of course, not algebraic, not polynomial, but in degenerate cases like a rational Calogero-Moser system. This is the way how you solve this equation. The way that was found by Anshanetsky and Perelov ages ago. So theta here is the Riemann theta function defined by periods of differentials on the curve. U1 are periods of some differentials. So everything is given in quadratures in terms of the initial data. In that sense, I'm saying that the system is algebraically integrable. Now, the same integrability, because as I said, the equation I mentioned above are restriction of the flows. So they're, in that sense, restricting this spectral transform on the locus of turning points will solve you the same, in the same way, the equation of motion. The question is, what are the spectral curves corresponding to the locus of turning points and what are divisors? So the answer is given in terms of, in the following terms. So it turns out that the spectral curve corresponding to locus points are spectral curves with involution. So it's symmetric with respect to certain involutions. So it's explicitly parameterized by half of integral of motion, odd ones. And the divisor lies in the abelian subvariety, which is prime subvariety. Again, this picture is the same as before. We have a nicely defined structure on the space of half of the dimension, which is the set of coordinates qi. And it turns out that open set is isomorphic to the total space of algebraically, I would like to say it's algebraically integrable system, because it's, again, it's a total space of a bundle over the space of curves with involution, and the fiber is abelian variety, which is the prime variety of this fact. And the equation of motion are linearized by this spectral transform. The fact that the corresponding curve admits involution is very simple, because if you look at the matrix, Lux matrix, and use the fact that sigma function is an odd function of its argument, then it's easy to see that the Lux matrix possesses the following symmetry. Its evaluation of minus z is equal to minus L of z transposed. That gives you that the curve is invariant on the involution induced by its simple change of sign for eigenvalue k and spectral and a point on the elliptic curve. So in one direction, it's very easy. In the other, it's not so easy. The proving of this fact involves a new type of identity we found for the Riemann theta functions corresponding to smooth curves with involution. But it's far out of scope of this conference, so I will not present a proof here. So the odd flows, as I said, of elliptic Calogero-Moser system restricted to the locus of turning points are linearized by the spectral transform. So my question is, the restriction of elliptic Calogero-Moser system onto the locus of turning points, is it a completely integrable Hamiltonian system? So I presented this particular example. You have equation of motion This is the first order as it should be for Hamiltonian system. The whole phase space is fibered by abelian subvarieties, and these equations are linearized on these abelian subvarieties. The question: are these equation of motion Hamiltonian in any way? So, is there a Poisson bracket on the space of Qs? You cannot restrict the original Poisson brackets on this. It's Lagrangian, so you get identically zero Poisson brackets. So this is the equation. Looks very nice, and so both answer is not integrable. So there doesn't exist any reasonable Poisson bracket. It will be the first time in my life when I see this picture, dynamical system linearized by spectral transform and not being a Hamiltonian system. So I tried, I honestly say, I tried all naive attempts and also not so naive, failed. So the question, maybe for audience, maybe someone is clever than me, say, is there a Hamiltonian interpretation of this equation, particularly this system, equation of motion, how to find non-trivial Poisson bracket of the space of Qs. And we'll see that these systems increasingly appear more and more often. So I think they are important on their own turn, but because most of participants of this conference are interested in quantum version. So is there a quantum version of the locus of turning points for elliptic Kalogera-Moser system or elliptic Rosenach-Schneider system? Any questions?
Can you answer this question in hyperbolic settings, so for trigonometric?
No, even in a rational case. You see all what I'm saying about elliptic case that generates nicely to hyperbolic and rational case. So you can replace in the equation I wrote Weierstrass function by 1 over xi minus qi minus qj squared. Again, this is integrable algebraically. Now it would be algebraically, really algebraically integrable system. But is it Hamiltonian?
I just have a quick question.
Sure.
Is the number of coordinates n, and is it just an arbitrary integer? Is it even number?
It's a good question. There is a certain difficulty, distinction between the case of odd and even n. And here is the arbitrary. So you take n particles, Hamiltonian system. So
if it is odd number, if it is odd number,
if it's odd number, it looks like it's not it's Poisson manifold. So there is a Casimir, and so you just reduce by 1 degree of freedom, and still you have even number of coordinates.
I see. Thanks.
So. And especially in that case, the dimension of the spectral curves is one more than dimension of the fiber in the case of odd n. So it's, again, everything looks nice and fits perfectly with our understanding how should integrable system looks like. But again, I will be happy to find an answer to my question, even in rational or trigonometric case. Okay, now I want to describe the connection of these systems with known soliton system, 2+1 dimensional systems with symmetries. So the first one that was introduced by Date Jimba, Krichever, and Miwa many years ago in middle of 80s. And it was called CKP hierarchy. And it's a hierarchy, usual KP hierarchy. A part of it, again, you take only odd flows of hierarchy and restrict them, because it turns out that you can restrict them on the locus of anti-self-adjoint pseudo-differential operators. So the usual phase space for Kadamson-Petriashvili system is a space of all pseudo-differential operators. Now you're taking the locus of anti-self-adjoint. This locus is destroyed by even flows, and it remains invariant with respect to odd flows. So each solution of the CKP hierarchy has a unique extension to the solution of the full KP hierarchy. So you start with the locus and you move it by even flows. You get the solution to the KP hierarchy. So how to characterize these turning points, if you wish, because the answer suggests that that should be the right name for the CKP hierarchy. It's a turning points of KP hierarchy. So it turns out that tau function, KP hierarchy, is a tau function of such an extension. If at t equals 0, its T2 derivative vanishes. Again, it's not KdV. Of course, KdV is a particular subset of these turning points for Kp. But this equation holds identically for all T2. Here, we just at the first moment, at one moment, and this is the distinction between stationary points, reductions of Kp, to the case of turning points. And the statement is that elliptic solutions to if you look on elliptic solutions to CKP, then their pole dynamics coincides with the dynamics of elliptic Kalogera-Moser system restricted to the locus of turning points. So this is the same bijection correspondence as between the full set of elliptic solution to KP and elliptic Kalogera-Moser system. So this restriction to the locus of turning points preserves this correspondence. So where somehow my slides with a description of turning points for Rosenau-Schneider system disappeared. Let's see if it will survive. So again, for 2D Toda hierarchy, the picture is the same. 2D Toda hierarchy is a set of commuting flows on a space of pairs of pseudo-difference, not pseudo-differential, but pseudo-difference operators. The flows are defined by Lux equations presented here. And we can define the locus of turning point for this system by the condition that the locus is described by the equation that the second operator is the adjoint, formally adjoint for the first operator up to conjugation. Actually, it's because this conjugation came into play because the normalization for which I choose for the 2D Toda equation is not symmetric. You can choose another gauge in which L and L bar are symmetric, And then that would be the locus of operators such that L bar is equal to L conjugate, not conjugate, adjoint. Again, this locus invariant, surprisingly, although C toda exists in the literature, this reduction of C toda we found and suggested in our joint work with Zabrodin has never been considered in the literature. And once again, this story is carbon copy of what I said before. You have a set of even and odd flows, and this locus is invariant under odd flows, and solutions of C toda hierarchy single out among all solutions by the condition again. This is the turning point condition, that this velocity at certain moment with respect to T1 and T1 bar variables. This is actually real physical Hamiltonian, H1 plus H1 bar. It vanishes. So on the side of Rosenar's Schneider system, again, this is the case when velocities of Qi with respect to the Hamiltonian H are equal to 0. In terms of original system for T1, this is equivalent to the constraint that Qi dot equals what I have on the right. Usually, you have here in front e to the power pi. So indeed, this constraint says that pi, the momentum, equals to 0. Again, the same picture. We have the locus, which is just the Lagrangian plane for the original Poisson brackets. You restrict the equation, and it turns out that it is linearized by the spectral transform. The involution in this case looks a little bit more, not so simple, but it's still not far from what I described again. Again, the proof is involved. It requires some identities for the theta function, but the fact is very simple. Again, Rosenar-Schneider system, or odd part of it, restricted on the locus of 22, is algebraically integrable. The base space of this is fibered by three varieties of spectral curves admitting an involution. And the restriction of odd flows of elliptic Rosenar-Schneider hierarchy onto the locus of turning points coincides with the pole dynamics of elliptic solution to the C toda hierarchy. Again, it's the same as the statement we found many years ago with Zabrodin, that pole dynamics of two elliptic solution to 2D toda hierarchy is nothing more or less than the theory of elliptic Rosenar-Schneider system. Any questions? Okay. So it's far from the scope of this conference, so I'll be very brief on the next topic. I just want to present some abelian version. You see, it was so the theory of elliptic system is a theory of one-dimensional particles with interaction described by elliptic function. It was my old, not dream, but goal to find really multi-dimensional systems which are integrable in certain sense. And actually, it should be a system describing interaction of more than one-dimensional systems. And for that, I went to the theory, not elliptic solutions of KP or other equations, but to the theory of the abelian solution, more general type, when solution is given in terms not of roots of elliptic polynomials, but of a root of some abelian function. So, unfortunately, this system exists, but at the moment, its good understanding is far from being within the reach. So, along this way, I found that the abelian version of the path I described before leads to a solution of known problem, how to characterize Jacobians of curves with involution, not spectral curves of elliptic system, but general. You have an algebraic curve, you want to know when it admits an involution. The answer is given in terms of abelian generalization of this notion of turning point. So let me remind you the solution of Riemann-Schottky problem in terms of so-called Welter's conjecture. It says that abelian variety is the Jacobian of a curve with curve if and only if its Kummer variety has a trisecant line. So what is a trisecant line? Any abelian variety is embedded, not embedded with some self-intersecting points into the projective space of dimension 2 to the power g minus 1 through the explicit written theta functions of weight 2. So this is level 2 theta function given by just you double the matrix of B periods of matrix of B for original abelian variety with characteristics. So this is some embedding. And imagine you have embedding of g-dimensional space into the space of 2g minus 1. And the trisecant is the line that intersects this image at 3 points. So you take 2 points, you draw a line, and because it's g-dimensional is 2g plus 1 dimension, you don't expect that it meet the Kummer variety at the 3rd point. So, and this is the characterization. It's a long, long story how Welters come to this. There was a lot of intermediate steps, the famous solution proof of Novikov conjecture by Schroeder. I will not speak about this here. And actually there are 3 distinct cases of this conjecture formulated by Welters. It depends on configuration of these 3 intersecting points. So if all 3 of them coincide, it means that there exists a point of inflection point at which the tangent line is of order 3. If 2 points coincide, it means that there is a line tangent at 1 point meeting the Kummer variety at the 3rd one. And then there is, of course, the case when all points are distinct. It's a really trisecant. Of course, the first 2 cases can be seen as the generation of fully discrete case, the 3rd case. But if you have just one, not a family, just one trisecant, all these cases should be treated separately, and they were treated separately in my proof of this conjecture. And for the proof of all 3 cases, I used 3 main soliton hierarchy. The KP for case I, 2D order for case 2 and bilinear discrete Hirota equation for case 3. So 3 different proofs. Technically, they're different, but the idea was the same. So now, how to characterize now, due to the Walter conjecture, we know how to characterize Jacobians among all other abelian varieties. But how to find among them those that correspond to curves with involution? And the answer is given in terms of the abelian version of the turning point, namely, so the abelian variety is the Jacobian of the curve with involution if and only if the first equation holds. So there are vectors u, v, some constants such that this equation holds. And that equation tells you that, you see, there is a relation between first derivative, second derivative, and that tells you that this point a over 2 is the inflection point. So the case 1 in my previous list. And in addition, so this singles out this equation, singles out Jacobians. To single out curves with involution, you impose the condition that theta function restricted on the locus of zeros of, so on theta divisor, or better to say, the derivative of v in v direction of theta restricted to the theta function, theta locus is 0. This is a abelian version of the same fact. This is the turning point of this. I hope in some future would be abelian Kolodgero-Moser system. So this is the characterization. For the sake of brevity, I didn't present here the similar characterization that you can get from the abelian version of the Roisenar-Schneider system. Now, this is the story about turning point. Now, I want just to very briefly to describe how, to our surprise with Nikita, we came to this notion, trying to solve the problem about sigma model, double periodic. So the world sheet is a torus, and the sigma model with target space, which is the sphere with standard induced metric on it. So this is the action, and critical points of this action are harmonic maps of this elliptic curve into the sphere. And if I'm, to the best of my knowledge, the first solution to O4 model, which is the same as U2 principal chiral field model, was obtained by Hee-Cheol. And he used zero curvature representation for principal chiral fields found by Palmayer, Mikhailov, and Zakharov. And he made two remarkable observations, namely, so this is the zero curvature representation of equation of motion. So it's compatibility condition of two linear problems. You solve this system and look on the monodromy of the solution along the cycles. So you consider characteristic equations. They define some analytic curve. But it turns out this analytic curve, because its dimension is 2 by 2 matrices, so it's two sheeted cover of lambda plane. And the first remarkable observation of Hee-Cheol was that the branch points of curves defined by the characteristic equation First of all, they are the same for both monodromy matrices. And most importantly, there is only finite number of them. The matrices are, its entries are entire functions. So having only finite number of branch points, it was a surprising fact. And the corresponding hyperbolicity curve was called the spectral curve. So the solution to O4 model was given in terms of this spectral curve and certain device on it. Unfortunately, and this is the same kind of difficulties as in solving, for example, famous NUM equations. You can reconstruct from the curve and devise on it some solution to the equation of motion. But it's very hard to implement periodicity constraint. In general, this x of ZZ bar, which is a solution to the equation of motion, would be quasi-periodic. It's not periodic. And the equation of the single out algebraic data corresponding to periodic solution are transcendental. They are given in terms of periods of certain meromorphic differentials on gamma. So it is so hard to control that Hee-Cheol found solution for this equation only for spectral curves of genus 1, 2, 3 only. How come to that difficulty? It's typical difficulty. Imposing periodicity condition is very hard. Another observation of Hee-Cheol was that you can consider O3 model as a restriction of O4, just locus of fully geodesic maps. And it turns surprisingly, it turns out that the corresponding curve, spectral curve, that was observation by Hee-Cheol, is trivial. So you cannot get solutions to O3 sigma model through this spectral transform. At the same time, the solutions are pretty well known. They were obtained by, they were called instanton solutions. So they're not harmonic, they're more restricted, they're instanton. And they're given by the formula, and they are all parameterized by arbitrary elliptic function. The degree of this elliptic function is the instanton number of the solution, the degree of a map of an elliptic curve onto the S2, which is the target for O3 model. So, actually, the result of Hee-Cheol was extended and generalized in different directions. So first it was generalized to the case of arbitrary end for arbitrary ON model. And again, originally, only part of the solution was obtained, namely, let me say, that the space of harmonic maps to this sphere admits an stratification. There is a certain invariance of the system, namely, consider the moments. It's very easy to derive from the equation of motion that if first moments vanish, then the next one is a constant. So if it's a constant, you go further. So we call harmonic maps with 2L, this invariant, which is not first non-zero invariant T2L. We call them double L harmonic. The double L harmonic maps with L bigger than 1 are conformal maps and corresponds to minimal embedding of a torus into the sphere. So the first solution for arbitrary end by Pinkel, Pettit, they were harmonic maps that are not conformal. Then, after very active period of time at the turn of this century, actually all harmonic maps, it was shown that all harmonic maps can be constructed by means of soliton theory from algebraic spectral curves. Again, like in Hee-Cheol system, you have algebraic spectral curve, but the locus of curves that correspond to double periodic sigma model solutions is controlled by transcendental equations, and very little can be said explicitly about these spectral curves. So until recently, this W infinity, which is analog for arbitrary n of instanton solution found by Polyakov and Belavin, remained out of reach of the soliton theory. The indifferent, actually the theory of such harmonic maps goes back to Alabi, and in different works that they were called pseudo-holomorphic, super-minimal, or isotropic. So they should be constructed by different means. The usual soliton theory is not applicable to the construction of these maps. It turns out that we were able to construct these harmonic maps via soliton theory in a completely different approach. I'm talking again about our work, original work with Nikita Nekrasov. This approach, maybe it's safe to say, this is Lux-free approach for solving integrable systems. It's not applicable for all systems, but for a very large class. In order to explain the idea of this approach, I will go back to a very old paper by Cherednik, who observed that nonlinear Schrödinger equation can be obtained in two steps. First, you look on the linear problem, one-dimensional non-stationary Schrödinger equation with potential U. And then you said, okay, suppose U is equal to the norm of psi mod square. You put it into the equation and you got the equation of the nonlinear Schrödinger equation. In this approach, nonlinear Schrödinger equation is a part of the KP hierarchy. So, and it's typical when you have equation describing short and long wave interaction, they all have the same nature. You have a linear system with some coefficients and solution, and they are not related. Then there is a quadratic consistency relation, relates the potential of a linear operator with psi. This is exactly the type of equation we have for on or n sigma model. So the equation of motion are the following. It's a two-dimensional Schrödinger operator with, so the coordinates of the map sigma model are solutions to the two-dimensional Schrödinger equation with some periodic potential. And if you impose the constraint that it lies on the sphere, you immediately get the relation between the potential and the solution to the equation. So you plug in back to the equation, you got the solution, the equation of motion of nonlinear sigma model. So we found, surprisingly, that symmetries of two-dimensional Schrödinger equation that are described by that actually the famous Novikov-Veselov hierarchy preserve this constraint. So they provide symmetries to O and model. Probably I will skip mostly. So now, how do you solve this model in terms of this approach? You first look, forget about that U is somehow related to the solution. Look on the spectral properties of a Schrödinger operator, two-dimensional Schrödinger operator, with periodic potential. Then you can define the locus of Flaque-Blau locus, namely the locus which parameterizes solutions to the Schrödinger equation that are eigenfunctions for the shift for the monodromy operators. W1 and W2 are eigenvalues of the monodromy operator. Formally, this locus can be defined as by analytic equation. You just restrict your operator on the space of functions satisfying these monodromy properties. You get an operator whose entries depend on W1, W2. You write determinant of this matrix, and this is the equation of the analytic, infinite genus analytic curve. It's not so in general because this is infinite dimensional operator and determinant might not always exist. It turns out that it does exist for the operators we're interested in, and you have, in general, infinite genus analytic curve, Bloch-Flaque locus. So our main result with Nikita was that all spectral curves corresponding to solution of ON model are of finite genus. It's the analog of this finite number of branch points of the Hitchin result, but for completely different spectral curves. We use the same notion, but spectral curves arising from this approach are different from the spectral, probably different. Nobody knows how they're related to each other. So I'll skip the construction of these solutions corresponding to the case when the spectral curves turns out to be reducible. So in general, you have irreducible curve, but let's look on the spectral curves that are intersection of two is reducible. So it is a union of two curves. And it turns out that for this class of curves, the periodicity constraint, which I said in general are hardly P-controlled, turns out that they are effectively solved, and they are solved in terms of spectral curves. So each component of this reduced algebraic curve should be a spectral curve of Calogero-Moser, elliptic Calogero-Moser system. Again, I have no explanation how this theory of Calogero-Moser system appeared in the absolutely unrelated context. But it turns out that all solutions, and it turns out that solutions corresponding to reducible spectral curve are precisely this pseudo-galomorphic solution to the ON sigma model. And they're explicitly parameterized by spectral curves of turning points of elliptic Calogero-Moser system. So, okay, I'll skip it. It's maybe just some simple formula. So
Igor, what's W infinity stand for? So W infinity harmonic notes. W infinity.
You see, W infinity, WL. Okay. When W2, it's conformal maps. So we were thinking about what would be the Morris next type of curves. Imagine that it should be, instead of conformal, you think about W symmetry. So it stands for fully understood, probably, relation with double L geometry. Did I answer your question?
Yeah, thank you.
And W infinity, in that sense, something special. It's very special case. So I would be very interested to understand better this subject. So let me just finish my talk by saying that consider, for example, spectral curve corresponding to 2L particle system. It should be singular, and there should be certain singularity of this curve at the origin. So it's L minus 2-dimensional linear subspace in the space of all curves. Take theta function corresponding to this normalization and look at this formula. Okay. You may look or may not, it's just explicit expression in terms of theta function of this spectral curve of Calogero-Moser system. Then it turns out that if you evaluate this function at 2 points of the curve, it becomes this linear combination, becomes elliptic function of degree L. So we recover L instanton solution of the system. I have to say that as I said, this W infinity solutions as all harmonic, all solutions to the ON sigma model, they're invariant with respect to infinite number of flows governed by Novikov-Pisilov hierarchy. So if you write this hierarchy in terms of AI and BI parameters of instanton, it will be a very complicated system, dependence on these flows, which is linearized. So you put in Z some linear dependence on these flows, and they solve in the same way the system. Probably it's worth to write the explicitly equation of motion of poles and zeros of this W function. Probably it would be a new elliptic system as well. I'll stop here. Thank you.
Yes, thank you very much, Igor. Very interesting talk, a lot of new stuff to think about. Are there any questions?
I don't hear. There is a noise.
Yeah. Are there any questions? Thank you, Igor. Yeah. Yeah, I don't hear any, so I think, so basically you're saying that you talked about elliptic models most of the time because of they're most common, but you're saying many questions can be reformulated in terms of simple, like rational and trigonometric models. I think you can still ask this.
Again, here, just a reformulation in terms of, no, the last part of, which I presented as double periodic, it's elliptic case. Of course, there are some problems about solving ON sigma model with a world sheet being not elliptic curve, but say sphere. That is a kind of rational version of the story, but it's specific here. I don't know if this relation with turning points of Calogero-Moser remains valid in the case of a different source curve. But the rest, what I described in the first part of my talk about turning point relation to elliptic solutions to two-dimensional hierarchies with symmetries, it's pretty simple. Yeah, replace sigma function by sine, hyperbolic sine, not just by. Yes, that would be.
So, yeah, thank you. Other questions?
So I just want to return to my question. So is this system Hamiltonian? first? And is there any counterpart of what I said about these elliptic turning points systems in the quantum setting? That's all. I'm very interested to hear the answer.
Yeah, thank you very much, Igor. Okay, good.
Thank you.
So yeah, so I think we should go to the next talk. So Andrey, are you ready?
Hello, everyone. Yes, I think I'm ready. So can I share the screen? Yeah, we can see the notes. Yeah. Good. Okay, so yeah, so Slava, so I have to go, so I'll leave you as the host, and everybody else is co-hosted with the speaker. So yeah, and then yeah, obviously everything will be recorded. All the videos so far, all videos of the previous sections are already on the website, so welcome to check them out. So please don't forget to email me your slides. I'll put them as soon as I get them online. Okay, so let's go to the next talk. Our next speaker is Andrey Smirnov from University of North Carolina, from NC State, and then he'll be talking about difference equations arising from elliptic stable envelopes. All right. Hello, everybody. So this is the title of my talk, and so let me maybe say a few words about the general structure and the outline of the talk here. So what I'm trying to describe is basically the following thing. So I'm trying to start with some variety X, for which we have you know, a notion of elliptic stable envelope. So I'm not really assume any of you know any of those things, but the point is that there is a type of cohomology theory which is called elliptic cohomology. And recently, Akunkov and Aganagic in their work, they defined, so to say, a basis in this elliptic cohomology, which they call stable basis. And there is, you know, an open question how to describe the set of varieties for which such thing exists, for which stable envelope exists. And there are some, you know, nice examples. So we can talk about things which look like T star G mod P for some group G and some parabolic subgroup P. Things like Nakajima-Krichever varieties. And, you know, there is some list of known varieties, but as far as I understand currently, it's not known how to describe, you know, this set of varieties for which we can talk about stable envelopes in full generality. But again, I don't expect you to know anything about stable envelopes and algebraic topology like equivalent elliptic cohomology. I will try to avoid talking about this much in this talk. But the point is that once you have this basis, stable basis, you can study transition matrices between different types of bases in elliptic cohomology. And we want to think about these transition matrices between stable bases and elliptic cohomology as monogamy matrices of some Q-difference equations. And it turns out that those Q-difference equations are in a sense rigid. Rigid in the sense that once you know the monogamy of this type of Q-difference equations, you can reconstruct the Q-difference equation itself. So in the sense that we can use elliptic cohomology to reconstruct the form of Q-difference equations. And the Q-difference equations which arise in this picture, they're quite remarkable. For instance, once you start with, you know, Nakajima-Krichever varieties, you can get things like quantum Knizhnik-Zamolodchikov of equations associated with quantum loop groups. You can get things like quantum dynamical equations discovered by Etingov and Varchenko. Or if you start with T star G mod P, basically you arrive to McDonald theory. So McDonald Q-difference operators associated with, this type of groups. All right. So in this sense, this approach, it looks sufficiently general, and in the sense that you can start with any stable elliptic stable envelope, and there is always associated Q-difference equations. And those are interesting. So let me start again. I'll try to start with the most simple example of this procedure. So here I outline some steps, and this is the example in which all these steps can be understood in, on the most elementary level. So let's start with the following Q-difference equation. So here psi is just a scalar function of a variable z, and m, well, is this function. So in fact, this Q-difference equation, well, it actually has some enumerative meaning. So in fact, this is so-called quantum differential equation, which arises in enumerative geometry of quiver varieties. So basically, you want to count a curve. You want to do a K-theoretic curve count in quiver varieties. So some sort of quantum K theory. And this guy, this psi, is some sort of Giventhal's J function associated with that theory. And the quiver variety we actually are dealing in this case is, so to say, T star P0. So it's actually just a point. But it's not important, but I just want to say, like, even for some trivial quiver varieties, you can have some non-trivial Q-difference equation. And this particular Q-difference equation with this type of M appears in the enumerative geometry of this variety. Well, okay, so the point here is that if you look at this very simple scalar Q-difference equation, we can find two solutions of that equation. One solution is holomorphic near z is equal to 0. So it's just given by this infinite product. So if you just look at this infinite product, it should be quite obvious that it satisfies this equation with this n. Right? And I assume that Q here is a variable, is a complex parameter with absolute value less than 1. So this infinite product converge. Well, and it converges to some holomorphic function in the neighborhood of z is equal to 0. You can do exactly the same and try to construct solution of this Q-difference equation near the point z is equal to infinity. So just again, it's very simple to show that, modulo this non-analytic factor, which, I don't care about, the solution is given by the same type of infinite product, but z now goes, z is replaced by inverse power of z. Right? So again, it's elementary to check that this function satisfy the original equation. And then what is monodromy? Monodromy, by definition, is the transition from solution near infinity to solution near 0. So it's just a ratio of these two solutions. So it's like Q periodic function on Z, which describes a transition, I would say matrix, but in this case, this matrix is just 1 by 1 matrix, which is just given by a ratio of these two guys. And from this explicit formulas, it's obvious that the ratio of these two guys is given by a ratio of theta functions. So where theta function here is just this double infinite product. All right, so it's a Q-periodic function given by the ratio of two theta functions. So this is an explicit formula for monodromy of this Q-difference equation. Then the next question is, can we reconstruct the original equation? So this original equation from the monodromy. So if I know the monodromy, can I reconstruct the equation itself? And the answer is yes. And it is given, the reconstruction is basically given by the following procedure. So you can take arbitrary real number, W, and you can consider the following limit. So you take your monodromy, shift parameter z by q to the power w, and ask, what is the limit of this monodromy? So more precisely, how this limit depends on the choice of w. So in this case, we just need to compute the limit of a ratio of two theta functions, right? Shifted by where the parameters of theta functions are shifted by q to the power w. And the answer, so it's quite elementary to compute what this limit is just from this infinite product formula. And the answer is remarkable in a sense. So it's given by the following formula. So it turns out that if w is not integer, then the result is just given by this monomial in H bar. So in particular, it does not depend on the parameter z at all. So you will see exactly the same feature happening later on in a general situation. But in this one-dimensional case, this is what we need to note. And then if w is actually an integer point, you can find that the answer depends on parameter z. And what we get here as a prefactor of this H bar is exactly the matrix M. I guess it's matrix M inverse from the Q difference equation, right? So the limit look as follows. You have like a real line in which your parameter W lives. And in this real line, in this space, you have arrangement of hyperplanes. Well, in this case, this arrangement is just given by these integer points, just by integers. And the limit actually really depends on W in a sense. Is W is on a wall or it's generic? If it's on a wall, if you compute the limit to the wall, so to one of these integer points, we exactly get the information about Q difference equation. So we know, if we know this guy, and we know what is the original Q difference equation, right? So using this limiting procedure, we see that if you know the monodromy of Q difference equation from somewhere, then we can use this limiting procedure to reconstruct the Q difference equation itself. And then the next question is, okay, but where we know monodromy from? And in this story, monodromy came from geometry. So I would like to explain where this ratio of theta function come from geometrically. So geometrically, the long story short is the following. So as I already mentioned that the Q difference equation, which we discussed, corresponds to a trivial Nakajima variety given by T star P0. It turns out there is a variety which is called symplectic dual of that, which I denote X trig. And in this very special and simple case, the symplectic dual variety is just isomorphic, it's just a vector space, it's isomorphic to C2. All right. And then on this C2, we have a torus action, so that you know, the character of this C2 is given by Z and 1 divided by Z divided by H bar. All right. And then machinery of elliptic stable envelopes constructed by Aganajik and Akunkov provides you some elliptic homology classes associated with pictures like that. And basically, the elliptic homology, like elliptic stable envelope, is some elliptic homology class, which, roughly speaking, is the elliptic homology class of attracting set. In this case, I can assume that Z is like a character of a torus, which is corresponding to attracting direction in my C2, and then 1 divided by Z is the repelling part. So there are two types of elliptic stable envelopes. One is the elliptic homology class corresponding to this line, and an elliptic homology is just the answer is given by theta function of this character. And there is other elliptic stable envelopes corresponding to repelling directions. So by the same logic, it corresponds to this line here, and it's again just the theta function of repelling direction, of repelling character. And then the transition matrix in this, again, transition, this is not really a matrix, this is one matrix in this case. Well, it's just the ratio of these two theta functions. And this is exactly the monogamy which we want, which we discussed about, right? So this is exactly the monogamy we were talking about before in the previous slide. And so from this example, from this trivial one-dimensional example, it's already quite clear what I'm going to do, right? So I would like to do the same thing in general. So namely that I can start with any variety X, for which I can speak about stable envelopes. Then I say that, you know, transition matrices, as before, as in this example here, between different types of stable envelopes is, you know, for me it will be a definition, is a monogamy of some Q-difference equation. And then I would like to extract the Q-difference equations themselves by considering these limits, right? So the generalizations of this limit we discussed here. All right. And again, as I mentioned, for Nakajima-Krier varieties, this procedure leads to some equations which describe enumerative geometry of these varieties, namely the quantum cosmology and quantum K theory of these varieties. And if you're talking about things like T star G mod P, you get something like McDonald theory associated, well, actually it's a McDonald theory associated with Langland's dual of G, but it doesn't really important at this point. Oops. Okay, so what is the difference between the situation I just described and the case of general X? Well, okay, so let's start with some X for which we know that the stable envelope exists. Well, this is, you can characterize implicitly these types of varieties, and the, you know, the set of necessary conditions on X can be found in this paper by Akunkov, but I'm not going to talk about that. So I just assume that X is a variety for which stable envelope exists. Then further, I assume that well, if you have a stable envelope on some variety, then it at least it's already implies that you have some action, you have an action of torus on your variety. So I denote this torus by T, because in the end we're going to talk about equivariant cosmology, So we really need an action of some torus here. And I assume that with respect to action of a torus, the set of fixed points on my variety is finite. And I denote the number of points n. So really the difference between the previous case, which I described above, and the general case is that all the monodromies, solutions, and equations, they will be matrix equations. So they're not going to be scalar, but they will be n by n dimensional matrix equations. So it's going to be rank n q-difference equations. And then we will have a bunch of parameters which appear here. So first of all, we have parameters a, which correspond to coordinates on our torus. They're usually called equivariant parameters in that kind of theories. And we have other parameters which corresponds to coordinates on a second cohomology of X. So in this story, they usually called Kähler parameters or dynamical parameters, depending on the context. All right, and so what is, in this case, if we have all these, what is the machinery of Akunkov and Eigenalgebra? What is this machinery of elliptic stable envelopes and elliptic cohomology provides? Like without going into details of elliptic equivalent cohomology, the procedure gives the following thing. So the elliptic stable envelopes of the fixed points are described by n matrix. So you can take a fixed point lambda, you can compute its elliptic stable envelope, which I denote stub plus here. Well, it's an elliptic equivalent elliptic cohomology class, and you can restrict it to some other fixed point mu. In this case, you'll get n by n matrix. So I sort of try to visualize this matrix here. And, by definitions of elliptic stable envelopes, which I never describe here, this matrix is, if you order fixed points in a special way, it's always upper triangular. And the matrix elements of this matrix, well, there are certain elliptic functions in parameters z and a, in equivalent and Kähler parameters. Okay. So in most cases, like type A Nakajima varieties or T star G mod B, we can actually compute these matrices quite explicitly, and they are given by some combinations of elliptic theta functions. So it's really a generalization of one-dimensional example, which I considered above. And then we also have a dual elliptic stable envelopes, which I denote by S minus here. So it's exactly as I discussed above. There are some attracting directions, there are some repelling directions, and if I trade attracting to repelling, I'll get opposite matrix, so to say. And this matrix is related to matrices plus by some transformation, which roughly does the following. It shifts all Kähler parameters by some powers of h bar and transpose the matrix. So if one matrix was upper triangular, so we have, in one case, I have upper triangular matrices of some theta functions. In the other case, I have lower triangular matrices of some theta functions. And this is give me what I want, right? So I want to define a monodromy as a ratio of these two matrices. So this is going to be a monodromy of some q-difference equation for me. And so you see in this approach, monodromy really shows up together with its natural Gauss decomposition, because one matrix is upper triangular, second matrix is lower triangular. And I want to think about this object, which I can obtain from geometry as monodromy of some q-difference equation. All right, so this is what monodromy is. And to reconstruct q-difference equation, I do exactly the thing I did before. So I want to shift my Kähler parameters by q to the power w. Now w, of course, is not one-dimensional. It's not just a real parameter. Now w lives in real cohomology, second cohomology of X? Well, I assume that it's some S-dimensional vector space. I have some coordinates there. And so really by shift Z by Q to the power W, I mean like multi-dimensional shift. And I play exactly the same game as as in my example, which was on my first slide. So I want to analyze what is this limit. I want to compute this limit and see how it depends on the choice of W in this multidimensional vector space. But as I already know that the monogamy is the ratio of two stable envelopes, well, it's the same question as to analyze how to compute the limit of stable envelopes, of elliptic stable envelopes, as Q approaches 0 and you shift Kähler parameter in some direction by Q. Right? This is again a generalization of my one-dimensional case. This is the result we proved with a Yasha Kononov in this paper. And the answer is given in following terms. So again, let's say my second cohomology is S-dimensional space. So I choose, it turns out that this vector space comes together with some natural hyperplane arrangements. So I tried to depicture them in this way. And so the limit, which depends on a choice of W, so W is just a point in this vector space. So the limit really depends on there are really two possibilities for that limit. One possibility is that W is not on one of these walls, so W is generic. And the other case is when W actually hits one of these walls, or maybe like intersection of several walls. And the answer is the following. So when W is generic, so when it's not on a wall, the answer is already given in the paper by Agunkov and Agamagic, and that situation is called K-theoretic limit. And in that case, it turns out that if you consider the limit of elliptic stable envelope, well, you'll get some answer. It's going to be again some upper triangular matrix. But the point is that this upper triangular matrix does not depend on half of variables, right? So you lose all the dependence on Kähler parameters. And what this matrix is, well, it also has a geometric interpretation. It is a so-called K-theoretic stable envelope with a slope W. So again, I'm not going to talk about it, but it's some object which is now lives in equivalent K theory. So elliptic cohomology in this limit degenerates to K theory, and we'll obtain some classes there. So this matrix is just matrix of restrictions of these K-theoretic stable envelopes of like point lambda to point mu. That's going to give you n by n matrix. But this is not really the limit we want, and we want really to analyze the situation when W is on a wall. And so this is what we did with Yasha. So we showed that a quite remarkable thing happened. So now, if W is on the wall, this limit depends both on Kähler parameters and equivariant parameters, but it depends on them in a remarkable way. So this limit actually factorizes to a product of two matrices. One only depends on Kähler parameters, and the other is depends only on equivariant parameters. So it's a quite remarkable thing if you think about that. It's never happened by random, right? So if you have some limit, which is n by n matrix with rational, whose entries are rational functions in Z and A, what is the chance that this matrix factorizes to a product of two matrices, which depends on half and half parameters. So at random, it never happened, but with elliptic stable envelopes, that's the case. Right, and again, A is as before, so it's the same K-theoretic matrix of K-theoretic stable envelope, but Z is a more complicated thing. It doesn't have immediate interpretation unless you have mirror symmetry. So if you have mirror symmetry, meaning that you know what is the symplectic dual variety, then secretly this matrix will be a K-theoretic stable envelope of symplectic dual variety. But for a moment, we don't really need it in this talk. Okay, so we have this behavior of a limit of stable envelopes, and now we know. So I just recall that. I just want to say that this is just multi-dimensional generalization of my one-dimensional example. So let me, for 1 minute, go back and recall that in one-dimensional case, in this case, which everybody can analyze, we had exactly the same situation. We had one-dimensional space, which is, you should think about it as a second homology of X. And you have some hyperplane arrangements given by these points. And when your limit is generic, so somewhere not on a wall, you don't have any dependence on Z. But if you hit the wall, the limit actually depends on Z, and it gives you the operator N. So it's really a multi-dimensional generalization of the same thing, except that one new feature arises that these multi-dimensional matrices start to factorize. All right, so I have this, but now let's go to original question, how to analyze the limit of monogamy. So as I mentioned, if you want to compute this limit of monogamy is the ratio of two stable envelopes, and we know the limits of stable envelopes. So if you go to the wall, so if you choose W on the wall, then the limit of this guy factorizes to a product of matrices Z and A. The limit of this guy factorizes in a similar way. And so what we get here, I want to denote this matrix in the middle, which depends only on parameter Z, by BW. So for any wall, I have this, operator BW, which I want to call the wall crossing operator. Right? So if you think about that limit, so what I said already, that matrices A here, A plus and A minus in these pictures, they are matrices of K-theoretic stable envelopes. And so if you do some linear algebra, what is written here is basically says to you that these wall crossing operators, they are operators which act in equivalent K theory of your variety. So we get some operators which in addition depend on some extra variables or on some parameters Z. All right, and so if you have these parameters, if you have these operators, you can prove that they actually satisfy remarkable properties. So here's the theorem. So perhaps the most important one is the following, that suppose you have some path in your second homology, which connects 2 points A and B. So in this picture, so I have 2 points A and B. I have 2 different paths connecting them, for instance. And then you want to define a product of wall crossing operators, again, which you define by this way, through the limit. Then it turns out that if you compute the product of wall crossing operators along, say, the path gamma, So it's a wall crossing operator corresponding to this wall, to that wall, and that wall. Or the wall crossing operators, the product of wall crossing operators over the second path, then it will be the same operator in the end. Right? So the product of them does not depend on the choice of paths, and it only depends on initial and final point. And that is exactly the property you want to construct Q-difference equations. Because this theorem basically implies the following. It basically implies that you can construct Q-difference equations in the following way. So the construction is the following. Suppose you fix an alcove in this space. So this is going to be some alcove delta. And suppose you have a line bundle. A line bundle. Then you can shift alcove by this line bundle in the sense that you can take your alcove and add to it first Chern class of your line bundle. It's going to give you some other alcove. Like this one, or you can shift by some other line bundle, you get this alcove, doesn't really matter. And then I consider my original alcove and shifted alcove, and I choose any path which goes from first alcove to the second alcove. And for that situation, I define the following operator. So I call it M lambda. It's going to be a product of all wall crossing operators along the path. So in this picture, it's going to be a product of two wall crossing operators, this guy and this guy. And I, in addition, multiply it by line bundle. So the whole thing is acting in the K theory of X. So I already mentioned that wall crossing operators, they are elements of this space. They act on K theory. And by L here, I mean the operator of classical multiplication, like tensor product by line bundle. So it's also an operator here. So why do we need these things? So why these operators are interesting? Because they have the following remarkable properties, which again follow from this independence on a path. So what we can prove about these operators is the following. Again, let's L be a line bundle, and let's denote a shift of a Keller parameter by Q to the power line bundle. So let's say, let it denote the following thing. So I just take each Keller parameter and I shift it by Q to the power first Chern class, first component of first Chern class in second cohomology and so on. So I just shift them by these components of L. And then if I have two line bundles, then the operators which I define this way satisfy the following property. So basically they form Q commutative system. Right? So if you take operator M corresponding to some line bundle prime and multiply it by operator M corresponding to some other line bundle F, but shifted by Q to the power L prime. It's going to be the same. It's going to be the same product if you switch roles of lambda of L and L prime. And it's going to be the same operator as just M operator corresponding to a product of these two line bundles. Right? So in other words, if you define the Q difference operators, the shift operators, which act by any function of Keller parameters as shift by Q to the power line bundle. And using these shift operators, you define the following Q difference operators. So it's my original matrix M by N matrix M. Multiplied by Q difference operator TL inverse. Then this equation basically says to you that these Q difference operators commute. Right? which means that these guys actually components of some flat Q difference connection. So this is exactly the, the structure you want to get. And so this is what we call Q difference equations. So again, the system of these operators labeled by different line bundles form a flat Q difference connection on second cohomology of X with fiber given by K theory of X, apparent K theory. So you can think about it as, you have a vector space, and so this vector space, and you have a trivial vector bundle over it with fiber given by K theory. And you have some flat connection defined by these deltas. And if you ask what is the flat section of this connection, well, they are a solution of these Q difference equations by definition. And this is exactly the Q difference equations which I want to get. And by construction of these Q difference equations, they has exactly the monogamy. So my goal was to construct certain Q difference equations so that their monogamy is given by elliptic stable envelope. Well, and you can prove, it turns out that you can actually prove a theorem that, so some sort of consistency check that it's exactly the case. So if you consider these Q difference equations, and you consider the monogamy of these Q difference equations, meaning that we have two regions in which you study holomorphic solutions of these systems. One is the region corresponding, to say Zi is bigger than Zi plus 1. And the other region is like opposite, so it's like a cone. So, and then you solve your, then you find the holomorphic solution. Then if you analyze the holomorphic solutions in that region and holomorphic solutions in that region, and then you ask what is the transition matrix between holomorphic solutions in these regions. So it's going to be some n by n Q periodic matrix. It turns out that it's exactly what you want. So it's going to be the ratio of these elliptic stable envelopes. All right, and so yeah, I finished a bit early, but that is basically the story. And so this is what we get.
Are you finished, Andrey?
Yes, I guess I'm finished. Yes.
Okay, thank you very much. Yes, indeed, we have some time for the discussions. So please ask Andrey questions or make remarks. I have some, but let's listen first. Other listeners. Anyone? Okay, let me pose the question. Andrey, could you please go to the first slide of your lecture?
Yeah, the most clear slide.
Actually, I like very much your talk because in scientific papers, usually people write in a very, very complicated way. You present it in a rather elementary one, and that's very good. So my question would be some kind of ideological one.
Mm-hmm.
Look at your first equation, the difference equation with m of z given by this example. To my mind, as far as I understand, the key point here is the fact that your m of z has good infinity and 0 points. So you have nice limits for m of z when z goes to 0 and to infinity.
Yes, that's right.
And because of that, you can do what you have presented.
Mm-hmm.
But let us suppose that m of z is an elliptic function with a different base parameter, p, which is completely different from q, independent of it. So that m of pz equals to m of z. In this case, you lose both points. You live on the torus, and there are no zero, no infinity points. And
so you want like more like elliptic generalization?
Yes, exactly. That's the story which we developed in our community for a rather long time now, for more than 20 years. And the point is that in this setting, you lose. Okay, you can take, for instance, as M of Z, your own monodromy matrix. And you lose, again, this infinity point and 0 point.
Yes.
And my question is whether you can say anything about the geometric picture behind this situation. Because analytically, we can say something about solutions, or some analytically, we have quite a lot, we know quite a lot about the system, but geometrically, picture, is it completely lost, or is it maybe something?
Well, I of course know about this problem, but I don't know how to interpret it geometrically. So the point is that, like, geometrically, this function, well, if you think about it as a power series, I guess it's something like h bar and q and zn, something like this. Well, this function is actually a generating function for the number of curves, well, so to say, in this variety. So, of course, in this example, it looks a bit trivial, but still, there is some enumerative geometry, like Gromov-Witten theory, which counts the number of curves of degree n in here. And it turns out that the number of curves of degree n is equal to this number. So it's not really a number because everything is equivariant. And if you look at the partition functions of the number of curves, you get this thing. So geometrically, we have an interpretation for this function as some sort of count of rational curves and varieties, like Quasimos. And at least this is how this, all this picture appear for me geometrically. But now you ask the question, now if I consider, elliptic generalization of these equations, what would be the elliptic generalization of Gromov-Witten theory? What is the enumerative theory which arises if I want to, substitute these Pakamer symbols by something like theta functions? And for this I don't know. I think it's possible, but I didn't think about it.
I can just, what I said, it looks like a kind of second quantization of this stable analogues, because as I said, take as of M of Z, your monodromy matrix, we should construct it. And now you repeat the same story with the matrix we have constructed from your ideology. But for instance, these psi's, they have an interpretation of superconformal indices in quantum field theories, which are actually the partition functions, which very nice topological interpretation. So all the expansions of the kind you just described, they exist, and they exist for the solutions of these equations. We know that it's very active and very now 15 years developing story about superconformal indices in relation to field theories. And so somehow it seems that there must be something in your geometric picture as well, in this kind of second quantization picture.
I can speculate a little bit about it. So, but again, there's going to be only, very speculative picture. So in principle, you may take something instead of X. You can substitute it by something like the space of loops in X, right? And say here on this space, you have some extra parameter, right? The parameter which you want to call P, I guess. So there is like an action of extra torus. So there is some extra torus S1 with equivalent parameter P, which what it does, it rotates a loop in this space. And then, okay, so you in principle, you can try to do exactly the same. And you want to now consider equivalent elliptic homology not of X, but equivalent elliptic homology of this bigger space. So in principle, it's like people discuss it. In principle, you may have some generalization to this infinite dimensional situation, but again, I couldn't really say much about this much more than that speculation.
It's a pity that Eric Reins cannot participate in our meeting. He's very busy. And I guess he has some thoughts about what can be hidden behind this picture, because he's developing a very rich mathematical theory of these systems. And unfortunately, I myself barely understand it. It's very complicated, but somehow it looks like he develops the algebraic geometry picture behind this psi of z or psi of z in this purely elliptic setting.
Well, yeah, like in physics, if you think about these psi's, well, they also appear as, partition functions of some supersymmetric quantum field theories. In this case, I'm talking about some particular types, like n is equal to like three-dimensional SCFT theories. And then there are some five-dimensional, six-dimensional generalizations of those, which people, and Peter in particular, always talk about. And they, correspond to some more like generalizations, like in this picture, what you really, as I mentioned already, in this simplest example, what you have is that these Pachammer symbols can get substituted by theta functions with this parameter p. But whenever I see those pictures, I couldn't really get much of geometry from there, but maybe it's just, I need to think harder. And I still feel like even in this picture, which I discussed today, not everything is yet clear and proven. So I feel like there are some things which, still can be completed here. For example, I never discussed in my talk today that there is actually symmetry between equivalent parameters and Kähler parameters, which is this three-dimensional mirror symmetry. And it means that exactly the same procedure I discussed today, when I consider it a limiting procedure in space of z's, can be applied to parameters A, and then you get some dual Q-different system of equations, which shift not Kähler parameters but z's, and presumably the systems you get, they admissible, so they commute with each other. But this is I don't really, at the moment, I don't really know how to prove it geometrically. So there are some still open questions even here, I would say.
Okay, Andrei, thank you for sharing your thoughts about this point.
Actually, can I make a comment?
Yes, Pavel, please. I was waiting for your reply because you are the expert.
Yeah. So actually, I discussed this question with Andrei Kunkov, exactly this question. So maybe let's
which question?
Oh, well, the question that Slava asked about elliptic generalization of these equations. So let us make the question a bit more concrete. So there are actually very rich family of equations which are elliptic versions of this, and which is the QKZB equations, which were studied by Varchenko, Felder, Tarasov, others. And they have very nice properties. They have integral solutions. They have bispectrality, all kinds of nice properties. And so I asked Andrei whether those equations have a geometric interpretation.
In my somehow world, they not even always exist. So somehow they exist only in the weight spaces.
That's right. Yeah. So I mean equations corresponding to representations of quantum groups. And so there is one difficulty there is that there is the zero weight condition. So the equations take place in a zero weight space of some tensor product of representations. And Andrei told me that he doesn't already understand how to make, what could be the geometric meaning of that condition. So actually, yes, I agree with your answer that it is not clear apparently, but there are very rich families of equations which are out there, and so it would be interesting to understand them geometrically. Yes.
Well, I understand this zero weight condition in a sense, like in a simple terms, like if you write these functions, say for some Nakajima-Krier varieties, and you substitute all Pachammer symbols by theta functions, like in a most straightforward way, then what you get is not even convergent in a sense. And then if you want your power series and Z like this to converge, you have to assume some sort of conditions, and they turn out to be like zero-wave conditions. But again, it means that if I want to apply and generalize my picture to the to geometry, it's not always possible. It's not really generalizable to like all Nakajima varieties, but to Nakajima varieties with very special, conditions. Or if you want to talk about cases like T star G mod P, you really don't want to take arbitrary P. You want to take only Borel, and so you get some zero-dimensional. So yeah, so I know those exist. I know they're interesting and nice, but they not exist in this generality we discuss here.
Okay. Thanks, Pavel, for helping to clarify certain points. It's quite interesting to me, and I guess to many others. Are there any other questions? Okay, I see that none. Then let's have a few minutes break, and whether Hee-Cheol is here. Hee-Cheol,
yeah, I'm here.
Okay, then let's start to prepare your talk, share your screen,
Okay.
and let's have, Andrei, you probably have to switch off your screen sharing.
Okay, can you see the slide?
Yes, the slides are here, but let's have a few minutes break. It was intense discussion and a good talk. Let's relax for a couple of minutes for all.
Yeah.
Okay, Hee-Cheol, what time is it on your side?
It's 12 p.m.
12. Oh, midday, I see. Okay, here we have 6 a.m.
Yeah. It's very early in your time.
Oh, manageable. Okay, I probably will say a few words. So people please switch on your computers. Yes, we can start now. Last talk for this session, and it's my pleasure to introduce Hee-Cheol Kim from Korea. I got acquainted with him at one of the elliptic meetings. I guess it was in Vienna, right? Yeah, he gave
in Vienna, and also I visited Moscow. Maybe 2018, I forgot.
Yeah, there was a conference in Moscow, so we already met a few times, and so in Vienna you presented very impressive talk. I hope this will be also similar one. So please talk about elliptic quantum curves of 6-dimensional superconformal field theories. You have your time.
Okay, thank you very much for the invitation to this wonderful workshop. So today I will talk about elliptic quantum curves of SCFTs. So this talk is based on the following 5 papers with Peter. Peter is here, I'm not sure, and also David Gaiotto and Matthew Brimmer who are attending this workshop, and also other people in Tsinghua and also KIAS. So this is my plan for this talk. I first start with a short introduction to the relationship between the Seiberg-Witten curve and the supersymmetric defect. Then I will introduce some simple supersymmetric defect in 6D superconformal field theories, and also explain how to construct them with some concrete examples. Then using such supersymmetric defect, I'll show you how to quantize the elliptic Seiberg-Witten curves related to the 6D superconformal field theories, and also give you some interesting examples, including 6D 2,0 A1 SCFT, and also E-string theory, and some higher rank theories, and then finish this talk. Okay, let's start with elliptic Seiberg-Witten curve over 6D SCFTs, which is classical in this slide. So Seiberg-Witten curve basically captures some low energy physics on the Coulomb branch or tensor branch in 6D theories of the moduli space. And these are some examples. So this is the classical Seiberg-Witten curve of 6D 2,0 A1 SCFTs. So we first consider this 6D SCFTs put on a torus with complex structure tau. Then the dynamics on the tensor branch of this theory is characterized by this classical Seiberg-Witten curve. In this case, since we put this theory on a torus, this Seiberg-Witten curve is kind of elliptic curve, including the elliptic function theta 1. Here, the curve is parameterized by 2 coordinates, x and y, and eta is the fugacity for the symmetry, and q is the elliptic parameter. On the right-hand side, we have w, which is a function of the tensor parameter. Later, I'll explain what this w means in 6D and also in 5 dimensions. And another interesting Seiberg-Witten curve is the curve for the 6D 1,0 E-string theory when it's put on a torus. And the curve is given by this. And in this case, the curve depends on the parameter mu L, which is the fugacity for the or chemical potential for the E8 global symmetry of the E-string theory. So in this talk, I'll talk about the quantizations of this kind of interesting elliptic Seiberg-Witten.
Sorry, what is U in W? What's relation with other parameters on the left?
Yeah, U is the tensor branch parameter in 6D theory. It's tensor scalar field, expectation value of the tensor scalar field.
And on the left, where is U hidden?
Oh, there is no U on the left side. But later, after quantizing this equation, you will see why we have a U in this side and why we have such complicated elliptic function on this side. Thank you so much for the question. Okay, Today I'll talk about the quantization of such Seiberg-Witten curve, especially elliptic Seiberg-Witten curves in 60 SCFTs using supersymmetric defect. Okay, so we will consider first codimension 2 defect in gauge series or field series and compute the partition function of the theory in the presence of codimension 2 defect on the omega background. Then we'll take necklace of Shatta-Shvili limit, which basically turn off the one of the omega parameter. Then it turns out that this codimension 2 defect partition function satisfies certain differential equation in 4D case or difference equation in 5D or 6 dimensions. This kind of differential or difference equations have been discussed in many literatures. So basic setup is drawn in this picture. So we consider, so basically we consider 60 theory, put on a torus times R2 times R2 plane, and we turn on the omega background. And we put the codimension 2 defect at the origin on R2 plane and compute the partition function and take the necklace Shatta-Shvili limit, which basically turn off this epsilon 2 parameter on the plane where we locate the defect. Then this defect partition function, which is denoted by Z, and it depends on parameter X, satisfy this differential or difference equation. So on the left-hand side, we have some Hamiltonian H hat, which is a function of X and X derivative. When we acted on a defect partition function, on the right side, we have another function, which may depend on X and also depends on U, which is a Kähler parameter, dynamical Kähler parameter of the bulk theory. And here X, which parameterize the elliptic curve in the previous slide, becomes a parameter of such as mass parameter or effort parameter living on the of the theory living on the defect. And this equation essentially quantize the Seiberg-Witten curve we saw in the previous slide. And furthermore, the difference operator H hat turns out to coincide with the Hamiltonian of the associated integrable system. So this is quite interesting story. So today I basically tell you about the role of this defective partition function for quantizing the Seiberg-Witten curve, and also its role in the integrable system. So let me give you a concrete example, which is very simple. So let's consider 5D n=1 theory with SU2 gauge group without any method. And it's known that this theory, the low energy dynamics of this theory is characterized by this classical Seiberg-Witten curve, which is very simple. And lambda here is the gauge coupling or exponential of 1/gauge coupling. We can introduce codimension 2 defect in this theory by simply coupling it to the extra 3D degrees of freedom living on the defect. So we put, so more precisely, we put the 3D n=2 Quiver gauge theory, which is now U1 gauge theory with 2 fundamentals to this location of the defect. This coupling can be done by gauging this SU2 flavor symmetry of the 3D theory by the 5D gauge field. Then we compute the partition function of this codimension 2 defect and found that the partition function Z here in the necklace of Shatta-Shvili limit satisfy the following interesting difference equation. Okay, here X hat and Y hat are the quantum variables satisfying this commutation relation, non-trivial commutation relation. And W here depends on U. U is again the Coulomb branch parameter of this SU2 gauge theory. And this W turns out to be the expectation value of the fundamental Wilson loop of SU2 gauge theory. Okay, so we can basically consider this equation as an equation introducing codimension 4 defect, which is now the Wilson loop expectation value. Okay, left-hand side, we have some difference operator, and when it acts on this defect parameter X, on the right-hand side, we'll have codimension 4 defect, which is Wilson. Okay. And if you compare this curve or this equation, difference equation with this classical cyber curve, then you see they are basically the same, but the coordinates in the classical cyber curve are promoted to the quantum variables in this difference equation. So this difference equation on the codimension 2 defect provide us natural quantization of the cyber curve for this 5D pure SU2 gauge theory. And moreover, it turns out that this H hat operator agrees with the quantum Hamiltonian of a two-body closed Q-Toda system or relativistic Toda system. And this eigenvalue is nothing but the fundamental Wilson expectation value. Okay, so our defect partition function provide concrete physical interpretation of or gauge theoretical interpretation of this Hamiltonian and also eigenvalue. And furthermore, this codimension 2 defect partition function now becomes eigenfunction of this quantum integrable system. Okay, so today I'll discuss, so this example basically illustrates the closure relation between the Cyber-Witten curve and also defect partition functions, and also the relation to the integral models. So today I will explain this kind of dictionary between Cyber-Witten curve and the defect partition function, and also integrable models for the 60 some interesting SCFTs. Okay, let me first explain the supersymmetric defect in 60 SCFTs. So we'll start with the half APS codimension 2 defect. As I explained, we put this defect and so it wraps the T2 and it's wrapping another R2 plane, but it's located at a point on the second R2 plane. And there are several different ways to construct such a half APS defect. So first way is to consider singularity of some gauge field or some field along a 2 plane. And this kind of defect is called Kukov-Witten defect. And second, we can engineer this defect by coupling extra degrees of freedom localized at the defect. In the previous slide, I gave you already one example by coupling 3D n=2 theory to the 5D bulk theory. And next, we can consider some Higgsing. So we can consider Higgsing of some UV theory by giving position-dependent vacuum expectation values on chiral operators. Then this expectation value triggers an RG flow to another infrared theory with the codimension 2 defect, because now we have the position dependence for the vacuum expectation value. So this is called Higgsing. And lastly, we can engineer this defect in string theory by using some kind of brains. Okay, I'll give you some concrete examples for these 4 different constructions. But interestingly, some defects have more than one way to construct. Okay, so the different construction can give the defect. We'll see the example. And these defects play very interesting roles in physics in various ways. For example, in duality and also quantization of Cyber-Witten curve and integrable models. Okay, I'll explain all these things for the codimension 2 and codimension 4 defect in my talk. Okay, let me give you one first example. Our first example is the codimension 2 defect inserted in the 5D n=2 SU2 gauge theory. Okay. This theory is known to describe the physics of 62,0 A1 type SCFT on a circle. Okay, they are kind of dual descriptions. In this theory, we can insert half APS codimension 2 defect using the monodromy on alt plane. So we'll consider a monodromy for this gauge field. In this case, then at the singularity where R=0, we can have non-trivial defect. And this monodromy defect is called Kukov-Witten defect. And it turns out that the same defect can also be constructed by simply coupling 3D n equal 4 TSU2 theory. This TSU2 theory is known as the duality interface or duality domainal theory in 4D n equal 4 SU2 gauge theory. But we can simply take the theory and put it at the location of the defect by gauging the SU2 flavor symmetry of this 3D theory. Then we can introduce codimension 2 defect. And it's known that these two descriptions engineer the equivalent codimension 2 defect. And this monodromy defect has a more generalization for SUN case with the generic monodromy parameter. This defect is described by coupling 3D theory given by this Krichever diagram, which is known as the TSU-N theory. And if you take n to be 2, then we get the TSU2 theory, and we'll consider by coupling this, we'll consider the codimension 2 defect by coupling this 3D theory at this point. And this defect has a brain construction in type 2B string theory and also type 2A string theory. Okay. This defect can be engineered by a D3 brain inserted by Hicksing or five-brain web for the UV theory, which is SU2 times SU2 with 2 by fundamentals. This UV theory has brain description like this. So it has SU2 times SU2 gauge theory with 2 by fundamentals. And you can Hicks this diagram to this diagram while inserting extra D3 brain between the web diagram for the SU2 gauge theory and the NS5 brain, which is moving pulled out away from this web diagram. Okay, this is called the Hicksing. And along the Hicksing, we can insert a single D3 brain at this point. Then this will insert a defect. In the field theory, it simply corresponds to giving a vacuum expectation value to the some operator formed by fundamental hypermultiplets. And the parameter x corresponds to the distance between this NS5 brain and this A brain. It becomes basically the Fi parameter in the TSU2 theory. And with this parameter x parameterize the position of this defect. And this brain construction has a dual description in type 2A string theory. In type 2A, 62,0A1 SCFT is engineered by 2 NS5 brains. And for convenience, we just insert one D6 brain along this direction. Then the defect corresponding to this D3 brain in type 2A theory is realized by a D4 brain ending on this NS5 brain. Okay. These brain descriptions are very good in a sense that we can read off the 2D 0,2 GRSM description for the self-dual strings living in this 60 CFT interacting with the defect. And using the GRSM description, we can essentially compute the partition function by employing the localization. Okay. And as I explained, the Seiberg-Witten curve also involved the codimension 4 defect. In this case, we will consider just the simplest codimension 4 defect. In 5D equal 2 SU2 gauge theory, we can insert the simplest defect, which is now the fundamental SU2 fundamental Wilson, which is defined in this way. We insert this Wilson at the point at the origin on R4 plane. And this gauge theory Wilson is described in the type 2A theory by or 60 theory by simplest Wilson surface operator carrying unit tensor charge. And it's realized in the type 2A string theory by an external D2 brain denoted by this red line. So this is a very heavy brain, so it becomes the defect. And this D2 brain realized this Wilson surface operator in 60 2,0 A1 SCFT. Again, using this brain description, we can read up the 2D GRSM for the self-dual strings or instantonic strings in this 2,0 theory coupled to the external D2 brane or the codimension 4 defect. So we are interested in the partition function and also difference equations satisfied by these partition functions. So we first need to compute the partition function. And as I explained, we can compute it using the localization based on the 2D, 2 Krichever gauge theory, living on K instantonic strings coupled to the defect. So before we insert the defect, we have a Krichever gauge theory for the self-dual strings in the M string theory or 2,0 A1 type SCFT. So this is the Krichever description for KM strings. We have a UK gauge group with some flavors, and here solid line denotes the chiral multiplets, and dotted line denotes the Fermi multiplets. So this is the Krichever diagram for the instantonic string without defect. But if we insert the codimension 2 defect, we'll have one more node with the U1 flavor symmetry parameterized by the fugacity X, and together with the one chiral multiplet and one Fermi multiplet. Okay, so this is the Krichever description for the self-dual string coupled to the codimension 2 defect. And using this Krichever diagram, we can compute the defect partition function. Okay. If we insert instead the codimension 4 defect, we have another Krichever node with the 2 chiral multiplets and 2 Fermi multiplets. Okay, so this is the Krichever diagram for the instantonic string coupled to the codimension 4 defect, and we can compute the partition function for this codimension 4 defect interacting with the instantonic string using this Krichever gauge theory by employing the localization. Okay. Okay, let me explain the quantization of elliptic Seiberg-Witten curve. So we will use the partition functions of the defect, codimension 2 and codimension 4 defect. But to see the difference equation or quantization of this elliptic Seiberg-Witten curve, we need to take the Nekrasov-Shatasvili limit where epsilon2 is sent to 0. Okay, and we will define codimension 4 defect in NS limit by psi. Now psi depends on X. X is the defect parameter or the FA parameter on the defect of the 3D theory living on the defect, 3D or 4D, depending on the dual frames. And U is the tensor branch parameter or the Coulomb branch parameter in 5D and equal to SCFT gauges. And also we define normalized codimension 2 defective partition function, which is nothing but the Wilson expectation value. And Wilson expectation value depends only on the Coulomb branch parameter or tensor parameter. Then we found that these two partition functions satisfy the following difference equation. Okay, so H hat is a difference operator. Here Y is the difference operator and X is the coordinate for the defect. When we add this operator on this codimension 2 defect partition function, then on the right hand side, we now obtain the Wilson expectation value times the defect partition function. Okay, so this one, as I explained, give you the natural quantization of elliptic Seiberg-Witten curve. So this is elliptic quantum Seiberg-Witten curve. And it turns out H hat is the Hamiltonian of elliptic two-body Louisiana-Schneider models. Okay, so our defect partition function and the difference of equation tells us very precise relationship between this elliptic Louisiana-Schneider model, integral model, and S5D n equal to SCFT gauge theory or 60 2,0 A1 SCFT. And in this quantization, epsilon1, which was one of the omega parameter, plays the role of the Planck constant H bar. And if you send this epsilon1 to 0, then this equation reduces to the classical elliptic Seiberg-Witten curve. And in this integrable Hamiltonian or the spectral curve, the eigenvalue W is nothing but the expectation value of the SU2 fundamental Wilson loop. And this is due to the codimension 4 defect in 60 2,0 A1 theory. Okay, so now I presented how to quantize the Seibel-Witten curve for the 62,0 A1 theory using the defect partition functions, POSTECH and W. And again, this POSTECH, which was the codimension 2 defect partition function, here in this integral model becomes the eigenfunction. And the same elliptic difference equation actually appears in completely different context. So let me briefly explain about it. So here we'll consider supercomponent index of now 4D class S theory coming from the 60A1 SCFT compactified on punctured Riemann surface. So we just take the 60A1 theory and compactify it on a Riemann surface and take the limit where this volume of Riemann surface becomes very small. Then we can engineer a 4D theory, which is called 4D class S theory. And we'll consider supercomponent index in this theory. And in this paper by Gayotto, Rastelli, and Rajama, they engineered half PS surface defect wrapping S1 times S1 in S1 times S3, which is for the supercomponent index. For this 4D class S theory, by acting a difference operator on the puncture. Okay. In this class S theory, each puncture carries SU to flavor symmetry. So we can turn on mass parameter for the flavor symmetry, which is now denoted by X. And they found that a difference operator called S here, when it's acting on this parameter X, we will have half APS surface defect in 4D theory wrapping S1 times S1. And this difference operator is nothing but this one, which is the Hamiltonian of the elliptic regional Schneider integral model, which I have shown in the previous slide, like this.
Can I ask you something?
Okay. Yeah.
So the X is the fugacity for the surface defect too?
It's a fugacity for the flavor symmetry in class S theory, coming from the puncture on the Riemann surface.
So it's one of the punctures. You have to choose.
Yeah, one of the puncture. Yeah, X. So for each puncture, you can assign different X. For example, in this case, we have 3 punctures. So you can assign X1, X2, X3.
Mm-hmm.
And this operator S can act either X1, X2, or X3. Okay, after that, you will get the supercomponent index for the half APS defect coupled to the 4D class S theory.
And choice of this puncture is also a data that defines surface defect.
Let me explain about it. So what is this puncture from the 60 viewpoint? In 60 dimensions, before you compactify, or if you zoom in around this puncture, then 60 theory locally look like S1 times S3 times R2. And this puncture is located at the origin on R2. So locally, it's some codimension 2 defect from 60 viewpoint. And this parameter X is nothing but the parameter for the codimension 2 defect in 60 theory.
Okay.
Does this answer your question?
I think so, thanks.
Okay, good. So this tells us very interesting relation between this difference equation for the surface defect in 4D theory and the difference equation we saw in the original 60 theory more directly, okay? As I explained, each puncture in this class S construction corresponded to, in 60 viewpoint, codimension 2 defect. And furthermore, the surface defect in 4D theory is just wrapping S1 times S1. So it has 4 transverse directions. So from the 60 viewpoint, it's Wilson surface operator or codimension 4 defect. Okay. So now using this dictionary, you can understand this equation precisely from the equation I have shown using the codimension 2 and 4 defect in 6 dimensions up to parameter identification of X eta q, in terms of t, p, and so on. Okay. So our defect partition function in Shikti theory tells us why we have this operator in this 4D class S series. So it explains this coincidence of appearance of two same difference operators in 6D and 4 dimensions. Okay, let's move on to another interesting example. So we will now consider 6D E-string theory, which is a theory with a single tensor with EA global symmetry. We'll consider 6D E-string theory on a circle. Then this theory is dual to 5D n=1 theory with S2 gauge group and a fundamental hypermultiplex. Okay, now we will consider the defect in this theory. We can first engineer codimension 2 defect in the brain system. So before we consider the defect, this theory, this E-string theory in type 2A string theory is realized by a single NS5 brain probing the singularity, OA singularity with 8D8 brains. And again, for convenience, we inserted this 6 brain. Then the codimension 2 defect is inserted by adding a single D4 brain attached to this NS5 brain. Okay. And codimension 4 defect in this case is realized by D2 brain attached, so infinity 2 brain attached to this NS5 brain. Basically, these two codimension 2 and codimension 4 defects are the same ones we used for the A1 2,0 theory. Okay. If you look at the local brain diagram, you can see they are basically the same defect. And this defect and their partition functions play the very important roles in the quantization of the Seiberg-Witten curve for the E-string theory. And from these brain descriptions, we can read off the 2D GLSM descriptions. And using the 2D GLSM, we will compute the partition function of this defect and see what kind of difference operator we can have. So defect partition function, when the Shikti theory is put on a torus in Nekrasov-Saakashvili limit, turns out to satisfy the following interesting equation. Okay. Here, the function u and V0 is given by very complicated elliptic functions, and a capital Y and capital X are the two quantum variables satisfying this commutation relation. And when this difference operator acts on this POSTECH is again the codimension 2 defect partition function in Nekrasov-Saakashvili limit. When we act this operator on this POSTECH, on the right-hand side, we will have the Wilson surface expectation value of the Wilson surface operator, which is nothing but the normalized partition function for the theory in the presence of codimension 4 defect. We can decompose this Wilson surface operator into two terms. First term only depends on X, which is now independent of U. U is the Coulomb branch parameter or dynamical Kähler parameter. And the second term depends only on U, okay, which is now independent of X. So we can naturally decompose this Wilson surface operator into two terms. And this difference equation contains elliptic Seiberg-Witten curve of the E-string theory. Okay. At the very beginning of this talk, I have shown the classical Seiberg-Witten curve for the E-string theory. And this equation is essentially the same as the classical Seiberg-Witten curve, except that the parameters for the curve X and Y are now promoted to the quantum operators. And furthermore, the difference operator D defined in this way, now including this elliptic potential term V0, is the Van Diezen operator. Okay.
Question?
So, yeah.
Is this the general Van Diezen operator? I mean, this 9-parameter system, or you have some constraints?
Yeah. This one has the most generic Van Diezen operator with A parameters for mu and also elliptic parameter.
So 9 parameter, the fully generic, because there was the work by Razamat where he was talking about, and he had some constraints, and now you have completely general situation. Then very nice. The immediate question: if you impose certain constraints on these parameters, which I will be talking about on Friday, then you come down to elliptic hypergeometric equation. Just from curiosity, can you say something about this situation or not when you impose some balancing condition when the Hamiltonian factorizes, or for you it's nothing special?
Very good question, but actually I haven't tried to specialize these parameters to see such a hypergeometric functions, but it's very good question. We have to look
because
at it.
In this case you have explicit solution for psi's. It's given by my elliptic hypergeometric function, and which is superconformal index of this SU8 Seiberg's theory. So it's very nice relation. Okay, thank you.
Yeah, it's very good question. Since we have, as you said, since we have formal solution for the most generic parameters mu, you can specialize the parameters and see if this psi reduces some interesting hypergeometric functions. It's very nice question. Thank you. Any other question? So this difference equation for the defect partition function tells us the precise connection between the Van de Graaff integral model and also E-string theory. And furthermore, in Van de Graaff operator, we have very complicated potential term. Sorry, this one. But here we gave a clear interpretation for this potential term, which is nothing but the self-dual string partition function. Oh, sorry, the one self-dual string partition function in E-string theory. Okay. So again, we can see the same operator in different contexts now in 4D. Okay, we will consider surface defect in 4D compactifications of E-string theory. Okay. And this surface defect has been studied in this paper by Nazar and Rajamat, and they discussed. They basically engineered this defect by some fixing, but they found that this surface defect wrapping S1 times S1 can be introduced by, again, Van de Graaff operator acting on the puncture. Okay, each puncture again carries acid flavor symmetry, and if we act this operator D, which is nothing but this operator, but specialization. So there is a parameter specialization. So they turned on only 4 parameters among these 8 parameters. But anyway, they found that the same difference operator, when acted on this 4-dimension superconformal index for S1 times S3 partition function with the puncture parameter X, then we get the superconformal index with the half EPS surface defect. Okay. Now so this equation now becomes very clear. We can understand the origin of this equation is nothing but this equation for the codimension 4 and 2 defect in 6 dimensions. Okay, because the puncture on this 4-dimensional theory construction using Riemann surface corresponded to the codimension 2 defect in 6D, and Wilson surface, which is a point-like object on the Riemann surface, and it just wrapped S1 times S1, now becomes a Wilson surface. It comes from the Wilson surface. Okay, so our computation shows a clear relationship between 2 difference operator appears in 2 different contexts. Okay, let's talk about the higher rank generalizations. Higher rank here means the 60 SCFTs include having more than 1 dynamical Kähler parameters. So the simplest higher rank 60 SCFT would be acid gauge theory with 4 fundamentals. And we found that codimension 2 defect and 4 defect in this theory can be engineered by essentially the same D4 and D2 branes in the brane system. And using the brane system, we could read up the 2D Krichever gauge theory description for the self-real strings and compute the defect partition function. And taking the NS limit, we found that the defect partition function, this codimension for 2 defect partition function and codimension 4 defect partition function satisfy this difference equation. And if you turn off this epsilon 1 parameter or the Planck constant, this difference equation precisely reduces the classical Seibel-Witten curve, elliptic Seibel-Witten curve for this theory found in this paper. And another interesting example is the 60 minimum SO8 gauge theory. It now have 5 dynamical Kähler parameters. And we engineered the codimension 2 and 4 defects in this theory and computed their partition function and checked that the defect partition functions satisfy the following interesting difference equation. And again, taking the classical limit where epsilon 1 is set to 0, this elliptic quantum Seibel-Witten curve reduced the classical Seibel-Witten curve for this theory found in this paper. Okay. As I explained, there is a very close relationship between the defect and difference operators in 6 dimensions, and also surface defect and supercomponent index in 4D series coming from compactifications of 60 SCFTs. So we can ask if we can have the similar relationship for the defects in 4D and 60s, even for higher rank 60 series. So let me briefly explain about, just leave some short comment about it. So in this paper by Gayato and Rajama, they constructed the surface defect in 4D class S2 theory, coming from the 60 S2 gauge theory with 4 fundamental flavors on punctured or Riemann surface, can be introduced by acting another interesting difference operator on the defect parameter or the puncture parameter V1 and V2. And this difference operator is quite different from the difference operator we found for this 60 theory. In our case, the defect basically has 1 parameter x. So this defect carries the U1 flavor symmetry. On the other hand, this puncture in this case, which is maximal, carries SU2 times SU2 flavor symmetry by construction. And the surface defect they found can be introduced by acting on operator for these 2 parameters. Okay, so this difference operator is different from the difference operator I found directly in 60 theory. So we have 2 different difference equations and 2 distinct defect, codimension 2 defect. So maybe interesting question is whether we can find some relationship between the codimension 2 defect or the puncture in this class S2 theory and the codimension 2 defect we found in the 60 theory. I think the relation is basically given by some kind of Hicksing, which break the SU2 times SU2 flavor symmetry for the puncture to the U1 flavor symmetry, but I haven't checked it yet. So this remains an interesting question. And another interesting question is if we can engineer the codimension 2 defect having SU2 times SU2 flavor symmetry in 6 dimensions corresponding to this puncture in this class S2 construction. And that would be very interesting question. And you maybe Regina already introduced 2 different difference equations for 60 SU3 minimal SCFT compactified to 4 dimensions. This difference equation has been found by Rajama for this theory, and also another difference equation may be explained by Louisiana. And the question is whether we can find or engineer the codimension 2 defect corresponding to the puncture with this symmetry. So in this case, we have 3 flavor fugacity, actually 2 flavor fugacities for SU2 puncture symmetry. And we can insert the surface defect in 4D theory by acting this difference equation And this differentiation has been proven to satisfy the kernel identity. Maybe it's already explained by Luigena. And it means there may be some interesting integral model associated to this G2 twisted compactification of 6S3 minimal SCFT. So yeah, it will be interesting if we can more directly engineer the defect and check this differentiation in 6 dimensions. And this is another difference operator to engineer the surface defect in for the theory of twisted compactification of 6D SU. Oh, sorry, this is SO8 minimal SCFT. And again, it will be interesting if we can find some related integral models, or if we can engineer some codimension 2 defect for this puncture in the 4D theory from the 6D SO8 minimal CFT. Okay, let me conclude. So we studied the supersymmetric defect in various 6D SCFTs and put on a torus and computed their partition functions on omega background. And we found that defect partition function in Nekrasov-Shapashvili limit satisfy interesting elliptic difference equations. And the difference equation gave us a natural quantization of elliptic Seiberg-Witten curves for the 6D SCFT. And moreover, this equation turns out to be the Hamiltonian of the associated integral systems, and the eigenvalues given by the expectation values of codimension 4 defect, and the eigenfunctions given by the codimension 2 defect partition function in NS limit. So the following interesting question we can ask. So, as we have seen, there are some integral models associated to 6D SCFTs, but it seems that maybe all the 6D SCFTs are related to some new integrable systems. So it's interesting question if we can find some way to identify the new integrable systems for each 6D SCFT, and also if we can construct systematically the BPS defect in 6D SCFTs, giving us the Hamiltonians of these integral systems and also wave functions. Okay, thank you very much for your attention. Let me finish here.
Okay, thank you, Hee-Cheol. Very nice talk. And please, some questions? Anyone?
Can I ask a question?
Yes, of course.
Yeah.
I have so you show the difference operator derived from the negative from partition function, and at the same time another difference operators that engineers the defect index when acted on the performing indices.
Yeah.
Can you explain why they have to be related?
Okay. So maybe my explanation was not enough. So let me explain about the string theory. Yeah. So maybe it's better to explain this. So this 4D class as a theory for 6D A1 theory is engineered by compactifying this 6D theory on a punctured Riemann surface. Okay. And maybe you know that this puncture is engineered by the codimension 2 defect in 6D theory, right? And if you zoom in, the geometry near this puncture, the geometry is nothing but the disk or the R2 with a singularity at the origin. And also around this geometry, you can try to identify what this parameter means. Okay, they carry some angular. So T is the fugacity for the n equal 2, or how do you say, n equal 2 mass parameter in 5D theory. And you can identify this T with the eta in this equation. And also P becomes elliptic parameter because you have S1 times S1. Okay, this P basically sorry?
In this picture, we have this 4-dimensional manifold across this Riemann surface as a volume 60 theory. I just don't see S1 plus S3. So where is S1 plus S3? Where is the S1 plus S3?
Oh, S1 cross S3 is the space-time geometry. So we have 4D theory. We put 4D theory on S1 times S3 to compute the superconfine index. So the full 6D geometry is S1 times S3 times Riemann surface.
In the previous slide, the 4-dimensional manifold was omega deformed C2, wasn't it?
Yeah. So let me explain about it. So if you zoom in again around this surface defect in this geometry,
Yes.
okay, then the geometry simply look like S1 times S1 times R2, transverse R2 on S3. Okay, times R2 here. Okay, in that case, the local geometry is essentially the same as omega background. And this computation has been done in my paper with Matthew, actually. So local geometry is T2 times R2. Local geometry, I mean the local geometry around this point on the puncture, and also this surface defect is precisely T2 times R2 with omega parameter. Q.
It's locally that, but the superconfirming index, no, it is a path integral on this S1. The whole
Exactly,
S1.
but this equation is acting on just the local puncture and inserting local BPS surface defect in superconfine index.
Okay, more questions? If not, then I will ask one.
Sorry.
Okay, go ahead.
I have a
Go ahead.
question.
Go ahead.
So hi, Hee-Cheol. So in the beginning, you showed a classical Eastern curve. So I wonder what is the relation to Sakai's classical Eastern curve?
Very good question. I wanted to try to identify this Sakai's Eastern curve and this curve, but it seems very complicated. I'm not sure if we can find some analytic reparameterization of the coordinate which deform this Seiberg-Witten curve to the form of this Eguchi-Sakai's Eastern curve.
I see. I see.
Yeah, it seems very complicated. But as an expansion, I think I could reproduce Eguchi-Sakai's curve as an expansion of parameters, but I couldn't find the full analytic reparameterization.
I see. By the way, the product here is from L equals 1 to 8.
No. In this case, we have plus minus. So this curve, in this curve, we made some specialization of this EA parameters.
Okay. It's a default.
So
default.
This curve, this curve was found in this paper. They basically considered the breaking of EA to SO times SO, SOA times SOA, and this mu L corresponded to the chemical potential for one SOA.
I see.
So we have plus minus. So we have 8 terms. But in our quantized string curve, we have full generalization of the parameters.
Okay, my question is exactly about this slide. So Hee-Cheol, the general solution of this n equal 1 division operator eigenvalue problem is not known, as I said, only this elliptic hypergeometric case. But the question is, what kind of physical information you can dig out from psi of x in your, suppose you know the answer, what kind of information you need about psi of x to get some interesting physical understanding?
So you are asking about taking some special limit of x?
Not really. Suppose you know psi of x for the solution. What kind of information you want to know about psi of x? What kind of physical information you can dig out from psi of x? So this is some formal equation, but solution is needed for understanding some asymptotics, whatever, compute some averages. In your case, what for you need psi of x?
Yeah, psi of x is basically defect partition function. We are interested in essentially the defect partition function itself. There is one important information. And
so
another thing,
asymptotics essentially, or whatever, or just the shape of that. That's what you want probably to know.
I think we are more interested in this eigenvalue WS. Right?
I see. So
yeah, eigenvalue is more interesting. In this case, we gave the formal eigenvalue. It means U here is not quantized. But maybe we can try to give very clear quantization condition for this U by using kind of necklace of Shatter-Shibelius quantization conditions and see the form of this WL, which is basically the quantized, the Wilsonov expectation value. This form would be interesting, I think. Of course, psi X, when you specialize it, it will
boundary conditions. Do you need some boundary conditions?
Function.
Boundary conditions.
Yeah. In that case, yeah, exactly. To have the normalized solution or normalized eigenvalue or wave function, you need to specify the boundary condition, which I haven't done yet. Yeah.
Okay, so it's not
because this is just formal solution at this moment. Yeah.
Okay, thank you. More questions? Still have a few minutes if someone is interested in. Okay, I don't see anyone willing to continue. So thank you, Hee-Cheol, for a nice talk. And thank
you so much.
Thanks to all speakers for this session. It was very interesting and intense. So let's rest for a while and see you for someone tomorrow, for someone today in the evening. So long until the evening. Hee-Cheol, could you please switch off? You are the organizer in the sense of the thing.
So it was very good to see you again.
Okay, yes. So goodbye to everybody until the next
goodbye.
session.
Yeah, bye.